Yeah, what's up everyone? Welcome to the 2018 USNCO local exam descriptive/laboratory section. So this is going to be from question 7 through 12. Let's start with question 7. Addition of 6 molar hydrochloric acid to which substance will not result in gas evolution? So we have 4 different options, and let's go through all of them. So first up, we have aluminum. Aluminum being reacted with hydrochloric acid. This is a single displacement reaction. The hydrogen gets left on its own, and the aluminum gets paired up with the chloride. I don't know the charges, so I'm just going to leave it like this, but one thing that we can't do is leave hydrogen on its own. Hydrogen has a 2 as a subscript because hydrogen is a diatomic element. And the thing about hydrogen in its diatomic form is that it's going to be a gas. So you do have some sort of gas evolution happening. The hydrogen gas is being evolved, so it can't be A. B, we have zinc. So zinc with hydrochloric acid. So the zinc gets paired up with the chloride, and zinc usually has a charge of 2+, so we're going to have zinc chloride 2 with hydrogen, and again hydrogen needs to be in its diatomic form, so this is going to be a gas. Can't be B. Let's look at C. So we have K2CO3 being reacted with hydrochloric acid. Now this produces H2CO3 and KCl, potassium chloride. Now the thing about the H2CO3 is that it doesn't like being in this form. Although currently it is aqueous, it almost immediately dissociates into water in a liquid form and CO2, carbon dioxide, which is a gas. So we do have some sort of gas evolution happening. Therefore, it has to be the last answer choice, but let's see why. So we have NaNO3 reacting with hydrochloric acid. This is a double displacement reaction, so you have HNO3, nitric acid, which is aqueous, and sodium chloride, NaCl, which is also aqueous. Therefore, you don't have some sort of gas evolving, so our answer here is D. Let's go to question 8. A divalent metal ion dissolved in dilute hydrochloric acid forms a precipitate when H2S is bubbled through the solution. Which ion isn't? Now, this question deals with a branch of chemistry known as qualitative analysis. Now, there's techniques in qualitative analysis, and all qualitative analysis deals with knowing the ions in a solution without having to do math or think about it quantitatively. There are techniques in qualitative analysis like adding hydrochloric acid or adding H2S in acidic or basic conditions, and depending on what type of steps you do, you will precipitate certain compounds. Now, this one in particular tells you to bubble H2S under acidic conditions. We know it's acidic because we're dissolving it in hydrochloric acid. Now, in qualitative analysis, when you precipitate certain compounds with the help of H2S under acidic conditions, the compound needs to have a group 2 ion in it. Now, group 2 ions include things like bismuth, cadmium, tin, and copper. And so if our problem tells us that something precipitated, then it must be it must be a group 2 ion. The only group 2 ion that we have here is cadmium, so our answer is D. So again, this is a technique in qualitative analysis where you can bubble H2S under acidic or basic conditions. In this case, we had acidic. If it was basic conditions, you would precipitate group 3 ions, and there's a whole branch of study based around this. All right, let's go to question 9. Which compound will form the most intensely colored 0.01 molar aqueous solution? The thing about this question is that we know that only compounds involving transition metals can be colored, and in this problem, there's only one answer choice with a transition metal in it. Chloride, oxygen, potassium, they're not transition metals. Potassium, aluminum, sulfur, oxygen, not transition metals. Potassium iodide, not transition metals. So it must be A. Manganese is a transition metal, and the manganese that we're dealing with here looks like manganese 7+, which forms a kind of bright pinkish color. All right, let's look at question 10. So a solution contains 0.1 molar strontium ions and 0.1 molar silver ions. Addition of an equal volume of a 0.5 solution of which reagent will cause precipitation of a strontium salt but not a silver salt. So for all of these answer choices, we know that the strontium and the silver are going to be pairing up with the anion. So let's go through all these answer choices doing exactly that. So for A, we know that that the strontium is going to be pairing up with the NO3, NO3. So that'll be NO3 and we have silver NO3 just on its own. So let me get rid of those parentheses. Let me just rewrite it then. So now what we have to do is look at solubility rules to find out whether or not any of these are soluble or insoluble. The thing is, if you look at your solubility rules, strontium nitrate is aqueous, and so is silver nitrate. So these are both aqueous. You don't have some sort of precipitation occurring, so it can be A. All right, let's look at answer choice B. So we have strontium pairing up with the anion, which is the fluoride. So you have SrF2, and you also have AgF, silver fluoride. The thing about strontium fluoride is that it is insoluble. It's actually a solid, but in silver fluoride, it is soluble. It is aqueous. So that matches the requirements of our question. So that tells us that B is the answer. But let's look through C and D to make sure that we have the right answer. So for C, you have hydroxide. So we have SrOH2, and you have silver hydroxide. Strontium hydroxide is soluble, and the thing is, it's moderately soluble, but I guess it still counts as soluble. And silver hydroxide is also soluble, so that can't be our answer. And let's check the last one. So you have strontium chloride, and you have silver chloride. Strontium chloride is soluble, aqueous, and silver chloride is insoluble, so it's a solid. But this is reverse of what our question asks us. We want to find what causes the strontium to be a solid and the silver to be aqueous. So A, C, and D are incorrect, and B is the right answer. Let's go to question 10. It asks us, which would be most suitable for measuring 2.7 mils of ethanol for addition to a reaction with acidified dichromate? One of these answer choices can be gotten rid of immediately, and that's going to be the beaker. The beaker should only be used for crude volume estimations, I guess. It's not really accurate, so you wouldn't use it to find the most accurate measurement. Now you have a 10 mil graduated cylinder, 10 mil volumetric flask, and a 10 mil volumetric pipette. The thing about the volumetric flask and the volumetric pipette is that they both only have one mark. So if you have a flask, let me just draw a flask like this. You would only have one mark at the top that tells you that you're at 10 mils. So although you might have 2.7 mils, and at 2.7 mils you might be around here, you would never know that you have 2.7 mils. There's not a mark here that says 2.7 mils. So the same thing goes for the volumetric pipette, and for that reason you couldn't use them. But for a 10 mil graduated cylinders, you have a bunch of markings on the side that tell you when you've reached certain, I guess, landmarks or whatever. So a 10 mil graduated cylinder would be suitable for measuring 2.7 mils. So your answer is A. Let's look at the last one. The molar mass of a solid carboxylic acid is determined by titrating a known mass of the acid with a standardized solution of NaOH to a phenolphthalein endpoint. Which errors will lead to a molar mass that is smaller than the actual molar mass? So before we even look at the answer choices, let's try to understand what is happening in this experiment. So you have some sort of mass of carboxylic acid, and that's going to be titrated. Now what that titration is going to do is that it's going to tell you how many moles of carboxylic acid that you have. Molar mass is going to be grams versus moles. The grams are going to stay the same. We're going to have the same amount of carboxylic acid that's going into the experiment. What can change is the number of moles. The number of moles is dependent on how well we do our experiment. So if the number of moles that we get is too high, your molar mass becomes smaller. And if the number of moles that you find out through the experiment is too low, then your molar mass is too high. So since we're trying to find out which one will lead to a smaller molar mass, we need to find the problem that will cause the number of moles to be inflated, that will be too high. So let's look at one. Some of the acid is spilled when being transferred into the titration flask. If some of the acid is spilled, then that means you're going to need less NaOH to titrate the whole thing. If you use less sodium hydroxide, what that tells you is that you have less solid carboxylic acid. If you have less, your molar mass is the number of moles is too low, and if your moles is too low, your molar mass is too high. So it can't be A. It can't be 1. Let's look at 2. The endpoint is recorded when the solution is a dark red color instead of light pink. A dark red when it comes to phenolphthalein tells you that you've added too much sodium hydroxide. If you've added too much sodium hydroxide, then that means that the amount of moles of carboxylic acid that you supposedly have will be too high. And if the number of moles of carboxylic acid is too high, then your molar mass is too low. So 2 does make sense. So the answer would be B, 2 only. And that's it for the 2018 USNCO local exam lab/descriptive section. I hope you were able to learn something. Hope this was helpful. And I hope to see you later. Thank you.